This is experiment 13 from Physics with Vernier, air resistance. If you take a coffee filter and drop it, the motion is interesting. You can see that it falls with constant speed. It's not like a ball or a brick that just keeps on speeding up. The coffee filter falls and the air resistance increases until it matches the magnitude of the weight, and because the net force is zero, the filter falls with constant speed. Now we can study this air resistance behavior by looking at the fall of one filter, two filters, three filters, because they all have exactly the same shape, but they've got varying mass. And we can make a model for the behavior of air resistance. It's familiar to everyone that air resistance or water resistance is a function of velocity. If you're moving slowly, walking through shallow water, it's almost as if the water isn't there. But if you try to walk quickly, the resistance becomes significant. Clearly, the resistance is a function of velocity. A simple model for air resistance would have the magnitude of the air resistance linear with velocity. Another slightly more complicated model would be to have the air resistance force proportional to the square of the velocity. If you take Newton's second law and our two models for the drag force, you can show that the terminal velocity will be proportional to the mass of the object for the linear air resistance case. And for the quadratic air resistance case, you can show that the square of the terminal velocity will be proportional to mass. This is a testable prediction that we can study using Logger Pro and a motion detector. So I've got a motion detector on some ring stand material pointing down at the floor. I'm going to plug that into my LabQuest, and I've got my LabQuest already connected to the computer. I'm going to open a file in the Physics with Vernier folder, number 13, air resistance. I'll do that now. Now, one thing that's not in the book, but I like to do with students, is to reverse the direction of the motion detector and zero it so that the floor becomes the origin of our coordinate system and the numbers increase as you go upward. That means that the resulting graph will simply be a measure of how far the filter is off of the floor. Let me show you how to do that. Open the LabQuest Sensors dialog by clicking up in the toolbar here. You'll see that the motion detector is reporting the distance to the floor with a positive number. If I can get the pop-up menu for the motion detector and first reverse the direction of the coordinate system. This will now make up as positive. Next step is to zero the motion detector with nothing under it but the floor. You can hear the motion detector click a bit, and then the live readout shows 0. After doing this, the motion detector will report the distance of the coffee filters from the floor. And this is something that most students find a little easier to understand than an upside-down coordinate system. Now let me use this setup to measure the terminal velocity for a variety of coffee filters. First, I'm going to take one filter, hold it under the motion detector, start data collection. So now we've got a graph of the position as a function of time for one coffee filter. You can see that at the beginning the coffee filter was held still, then it started falling, but almost immediately reached constant speed. If I select the constant speed portion of the graph and fit a straight line to it, I can see that I've got a slope of about 0.9 meters per second, and that's the terminal velocity for one coffee filter. I can do the same experiment for 2, 3, and 4 coffee filters, each time getting the slope of the linear portion. If I take 2 coffee filters, I can do the same thing. Start data collection, drop the filter. This graph shows position versus time for both one coffee filter, that's the red line, and 2 coffee filters, that's the blue line. You can see that the 2 coffee filters reached a slightly higher terminal velocity than did one coffee filter. We can find that terminal velocity by fitting a straight line to that linear segment, just like we did for one coffee filter. We can repeat that for 3, 4, 5, and more coffee filters and accumulate a table of terminal velocity as a function of the number of coffee filters. from that we can construct some other graphs. Here I've taken Logger Pro and typed in the number of filters in this column, the terminal velocities that came from the linear fits of my position versus time graphs, and that gave me a graph of terminal velocity as a function of the number of filters. That looks sort of linear, but is it proportional? Let's try something. Let's fit a line of proportionality to that. I'm going to use the curve fit function, and I'm going to choose the first choice, the proportional function. Click try fit, and OK, and I get the result on screen. It's not a very good fit. Now, the quadratic model predicted that the square of the terminal velocity was proportional to mass. So let's make a graph of that instead. In my data table, I've got terminal velocity and number of filters, which is the mass. But I need another column here. I'm going to take this opportunity to show you how to create a calculated column in Logger Pro. It's a very useful skill to have because you can apply this in all sorts of different experiments. I can go to the data menu and choose new calculated column. In this dialog, I see fields for a name, units, and also the equation field. And that's where the real magic happens. That's where I define the new column. So let me call this column velocity terminal, the terminal velocity squared. And I'm going to give it just the same short name, and it's going to have units of meters squared per second squared. Here's another little known feature of Logger Pro. These drop downs give you access to Greek characters and subscripts and superscripts. So here's a superscript 2, and I'll go divided by seconds and put in another superscript 2. Now down in the equation field, I need to choose my existing terminal velocity column, which is right there. And my calculation rule is just to take the square of that. So I've got the terminal velocity caret 2, which is to the second, means the terminal velocity to the second power, or the square. So I can click done, and you see in the data table that I've got a new column, and these values in blue are just the square of the values in red in the second column. To get this onto a graph, I can just take this column header and drag it over the y-axis of my graph, and that gives me my graph of the square of the terminal velocity as a function of the number of coffee filters. Now this one also looks like pretty much a straight line, but that straight line is heading toward the origin, which is very different from the upper graph of terminal velocity versus number of filters. Let's take this lower graph and fit a line of proportionality to it. So I've chosen curve fit. I confirm that the proportional function is chosen. I click try fit. I get a really nice fit there, and I can click OK. In the resulting graph, you can see that my line of proportionality fits the velocity squared data pretty well. This tells me that the model with the air resistance being proportional to the square of the velocity is the better fit. So we've tested two models for air resistance. The first with the air resistance force proportional to the velocity of the coffee filter, and the other with the air resistance force proportional to the square of the velocity. The second model fit the actual data much better. So it looks like we've got a reasonably good model for reality. If you study air resistance in more detail, you find that the model actually requires both a linear and a quadratic term. But for the terminal velocity of coffee filters, it looks like the quadratic model is a pretty good choice.